So I will go through a simple RLC circuit and creating a mathematical model and also a graphical model from that. And first we'll start with voltage outputs across the capacitor, then look at the changes in the equation when we take the voltage output from different points. So voltage output across the inductor and then the voltage output across the resistor. So let's get started. In the first case, we will look at the voltage output across the capacitor. To do that, we have these equations. Since it's a series circuit, the voltage is the summation of the components present, and the current equations are these. The voltage across the inductor is its inductance times the change in current. So in this equation, V out is equal to VC. So let's get started. So what we need to do is we want to replace the variables VR of t, VC of, and VL of t with a voltage output. So we can get one equation which contains voltage output and voltage input. So if we look at the voltage across the inductor, that's inductance times the change in current. We know that I of t is this equation. If we combine these two equations, we get the second derivative of the voltage output. And here, if we make voltage L the subject of this equation, we get VL of t is Vn of t minus VR of t minus V output of t. So VL we can replace by this equation. Voltage across the resistor, it's its current times the resistance minus voltage output of t. So now we want to replace this equation with something that contains voltage output. We know that current is already in that format. That's C dV out over dt. So we can replace that. So this is an equation which only contains voltage input and voltage output, and that's what we want to be able to create the graphical model. If we divide everything by LC, so this is our equation. We can use this to create the graphical model. So our voltage input is scaled by a coefficient 1 over LC. This goes into a summer, and the output of this is the second derivative of the output voltage. We'll label that with 2 dots. We integrate this, we get the first derivative, which is this, and if we integrate this further, we get the voltage output. Now this diagram is not complete. It doesn't contain the coefficients missing here. So this is a feedback system. So in this case, it's negative feedback. 1 over LC. So the output is scaled by 1 over LC and then fed back. Similarly, the first derivative also scaled by R over L. And this is also negatively fed back. So this is the graphical model of a RLC circuit if you take the output voltage across the capacitor. Next, we'll look at the output voltage across the inductor. Okay, so now let's look at the mathematical model when we take the voltage output across the inductor. The equations, these fundamental equations remain the same since the circuit hasn't changed. We are only changing the position where we measure the output voltage from. So like before, we focus on this equation, and now voltage output is equal to the voltage across the inductor. So now we want to make sure we replace VC of t and VR of t with voltage outputs. So we have one equation which only contains voltage input and voltage output. So we can look at the equation of voltage across the capacitor. So that's given by this equation. So VC of t is the integral of the current. So if we integrate both sides, we get this equation. And that's scaled by 1 over C. We know that we have another equation which gives us the current. So I of t here, if we integrate both sides, is 1 over L, the integral of the voltage across the inductor. Now we can substitute I of t into this equation. Vc of t is a double integral of voltage output. And it's scaled by 1 over LC. Now we can make Vc of t the subject of this equation. So that's V in of t minus VR of t minus the voltage output. And if we replace Vc of t with this, we can, to get rid of the double integrals, we can differentiate everything twice. That gives us t. So that will be double integral of the voltage input. And the same for the rest as well. So now we need to repeat the same process for voltage across the resistor. And we want to find this equation with respect to voltage output. So we already have an equation here we can use. So VR of t is current times its resistance. And the current, we've already found this equation with respect to voltage output. So we can substitute this here. but we want the second derivative of the voltage across the resistor. So we can double differentiate both sides to get equation. So that gives us the first derivative of the voltage output. We can replace this into this equation. So now let's make this the subject of this equation. So we have the highest power voltage output. Well, the second derivative as the subject. So this is our final equation. We can use this to create the graphical model as well. So there are two different types of models we can create here. First one uses you're differentiating the input twice. So our voltage input comes in and needs to be differentiated once and again. To get the second derivative. And this is the second derivative of the voltage output. We integrate this, we get the first derivative. And then integrating again gives us the voltage output. So I'm using the dot here to signify double differentiation or single differentiation. So that gives us the structure. Now we need to look at the coefficients. So voltage output is scaled by 1 over LC. It's a negative feedback. And the first derivative is scaled by R over L. The second way of creating this is by using, instead of differentiating the input like we did before, I copy this. So instead of having to differentiate the input twice, you can integrate everything twice and shift the differentiation to this side. So now the voltage input is not differentiated, but instead we have to differentiate the rest. The coefficients remain the same. So 1 over LC. And R over L. So To understand this more clearly, we can look at the equation. So if you were to integrate everything twice, you would get this equation. And this is what this equation is trying to accomplish. So at this point you are here you are double integrated the voltage output. So you have to differentiate once to get the first integral, and then differentiate again to get the voltage output. In this circuit, you're using differentiators, which is they're not ideal for any linear time invariant system. The reason is if you have any discontinuities in the signal, then the response of the circuit will be unstable. So usually it's not great to use differentiators. Now for the final circuit, we'll look at the voltage output across the resistor. So VR of t, voltage output t is VR of t. So similar to the previous two examples, we will replace VL of t and VC of t with the voltage output. Now to do that, we can look at the relationship between the currents. So you know that voltage out of t over R, which is this equation, is equal to C dVC of t. So voltage output is RC dt. Or a better way of showing this is, since we want to make the voltage across the capacitor the subject, 1 over RC voltage output. Similarly, the voltage across the inductor, you can say, so the current is VR of t. The voltage across the resistor is divided by its resistance. So we can replace I of t with this, so we get L d V out of t over dt. This is L over R. So now we can make VL of t the subject of this equation. We could choose to make VC of t as well the subject of this equation. But let's stick with VL of t. So VL of t, just replace that directly. So L over R voltage out is equal to Vn of t V out of t. So we already have an equation for the first derivative of the voltage across the capacitor. So let's differentiate this equation twice, so we can plug this into this equation. So this becomes the second derivative. if you replace this into this equation, you get an equation which contains voltage output and voltage input. If we divide the right hand side with L over R, so this is our final equation. Sorry, that's supposed to be 1 over LC. Okay, so now we can use this to create the graphical model. So our voltage input is differentiated and scaled by R over L. Differentiate voltage input and scale this. Here is our first derivative, sorry, the second derivative. If we integrate this, we get the first derivative of the voltage output, and then integrating again, we get the voltage output. And now we can look at the coefficients. So the voltage output coefficient is 1 over LC, and the voltage across the voltage for the first derivative, sorry, the coefficient for the first derivative is R over L. And finally, to end this video, I have summarized the differential equations and graphical models of the 3 circuits that we have looked at. The first one was the voltage across the capacitor. Here we are not using any differentiators. The second one is the voltage across the inductor. And finally, we looked at the circuit when we take the voltage across the resistor. So in the next video, I'll be creating the Simulink and MATLAB model for these and looking at the response of these circuits. Thanks for watching.